You ready for the final?
I think I am. I've been practicing quite a lot.
Do you know what's at stake?
Tea.
Absolutely. So 3, 2, 1, go.
Ow! Well, that was. I think that was the bat there. I think
It's got to be the
let me
bat. It's
down.
not the skill.
No. Yeah, I've been practicing for far too long.
Oh, the camera's on.
So what that was displacement.
Yeah, when you hit a teddy,
Yeah.
it goes like that, in that direction.
Yeah, and that can have a value.
It can.
And
So, because it's a vector displacement, it has both magnitude and direction, but also it has this neat little thing that can be divided up into its horizontal and its vertical components. Yeah. See, we don't just play around with teddies.
Now that's exactly what happens there, which is very handy, because this forms quite a familiar right-angled triangle.
It does. So if I hit a teddy that way, and I know it went 4 metres over there, and 3 metres high,
yeah,
then you know the resultant, just by Pythagoras, is going to be 5.
You do. That's very handy.
It's lovely. And this is common with all vectors. You can split it into its horizontal and vertical components.
You can.
However, what if I gave you more awkward values, like 6 metres across and 7 metres up? That's more awkward, because this isn't a 7 metre high ceiling.
Yeah, so that would first be impossible, and second, so awkward, Wayne.
Absolutely, got it.
Oh, so awkward.
Yeah, so what can we do at this stage? Because you could do 36 plus 49 square rooted, but that would give you an awkward surd or decimal.
Yeah, so that's not so fun. So what we can do instead is call these I and J.
Yep, it seems a bit silly. Ian and Jimmy.
Yep. So I, being the horizontal component.
Yep, so I go for a walk horizontally.
And, opposed to walking vertically. And I jump up.
Jump.
Yeah.
7. So this is 6. Because it's 6 across, and that's 7. And that is better than a surd or a decimal. That's a way of expressing the resultant of hitting a teddy in the air.
Yeah, and that's very handy a bit later on when we do resolving vectors.
It is. What if I gave you, in reverse, I gave you a thing and asked you to draw a triangle for it?
Okay, I can do that.
And it was 2i minus 4j.
Okay, often it's safe to assume, but they tell you anyway, most of the time, is that I is kind of east, so this way, and j is north when positive.
Yeah. So this one is positive 2, so it's going to be 2 going eastwards, unless it tells you otherwise.
Yeah.
But this is minus 4j, so rather than being 4 going up, it's now going to be 4 going down. And if this was minus 2i, it will be going back this way.
Yeah, so then you can write it like this.
And your right angle is always between the I and the j.
Yeah.
Lovely. So now we've got that sorted out, what sort of questions can they ask on this?
Well, they can ask to work out angles.
They can indeed. I think we'll stick to this example actually. I was going to rub it off, I think we'll stick to it.
Alright.
If they ask you to work out theta here, so the angle, say this was a cannon being fired off. We do parabolas later, but just say for a second it's a cannon being fired off. What's the angle it makes to the horizontal, so it's this angle here.
Okay.
That's how they'd word it probably.
Yeah, so you know from the 6 and 7 information.
That this is 6.
And this is 7.
So then it's back to GCSE.
Using a SOHCAHTOA. So we have the opposite and the adjacent, so we can use tan of theta is equal to opposite over adjacent.
Absolutely.
Yep, and once you've got that, then we can put those numbers in, I guess. You can do that next.
Yep, so tan theta equals, the opposite to the angle is 7 and the adjacent is 6. So the theta here, the angle it makes to the horizontal is tan to the minus 1 of 7 over 6, which I can't do in my head.
You know what, I can't either, so what I'll do is calculate it.
Well done you.
Thanks.
So then we can find out this angle. They might ask that for stuff like cannons and stuff like that. Throwing a ball. We also do parabola stuff later in the mechanics course for sort of the rest of the journey.
So that gives us 49.39.
49.39. Let's call it 49.
That sounds okay.
They might ask you to do it to the 0.1 degrees, so be sure to read the question, but normally, it's normally a good bet if they don't ask you to do that.
Yeah, they might ask something more complicated. They might ask the bearing that this displacement, this vector makes.
So I'll rub this off so that we can draw it in.
Yeah.
The bearing is slightly different.
Remember from GCSE, if you don't, here it is. It's always from the north line, which is always already up.
It is. And it's from the north line to the line that we're talking about.
Yeah,
so in this case it's this resultant here. And it's always clockwise, that's important. So we're needing to find out this, we'll call it theta subscript 2.
Okay, that works. So we can hardly do this in one step.
We can't, there's no easy way to just work out this theta.
No.
But what you can notice is that if this is perfectly horizontal and this is perfectly vertical.
The right angle there.
Well, indeed.
So that means that theta minus, or 90 minus theta will be r theta 2.
It will indeed. So if you 90 degrees minus, and work this out.
Yeah.
And if you hadn't in the question, you do it in exactly the same way. You'd work
Yeah.
out theta, 49.
And this will give us 31.
31 degrees, and that's not quite the
That's
answer.
not quite.
That is the angle here,
Mhm.
but it asked for a bearing rather
Yeah.
than an angle.
So when they ask for bearings, I like you to write it a different way. I mean, you can write it right. Yeah.
Yeah, you can write it. They like you to write 0.31 degrees.
Well, whatever the angle is, but in this form with a 0 in front, unless it's 100 and something.
Yep. So they want to see basically 3 units. If it's 31, the first unit is a naught.
Yeah. So it
And
could
assuming
go
you
up to
did the
3
working right and you showed your working perfectly, they
Mhm.
can condone if you miss off this degrees as well.
They don't mind too much, really.
If you just put bung down an answer and don't put any working, less likely they'll accept it. So just, I would
Yeah.
put a degree just to be perfectly accurate anyway.
Okay. So when you were in GCSE and you were saying doing bearings, when will I ever use this?
Now you feel silly because it's used right there.
Yeah, right
on
there when you're
ships
finding-
and stuff. If you buy a boat,
You buy a boat, or you just work on the boat.
if you work on a boat and you're given a message to a captain and you say 0.31 degrees, now that's wrong, and throw it out the window, and the boat sinks.
Yeah.
That's not good, is it? Really?
It's not good. So there's so many job opportunities with maths.
Absolutely. Yes. So you do use the bearings.
They don't just ask that.
No. And they don't actually ask the next thing I'm going to ask as I'm going to ask it. But what we're going to learn next is useful later.
Okay.
So if I threw the teddy over there
Right.
with this, what we've just been dealing with, this 6i plus 7j component,
And if I was over there and I hit it back,
you hit it back with another displacement thing.
so it ends up.
Minus 2i plus 10j, say, I don't know, say.
Where does it end up in the end?
That's what's the net displacement overall with these two things. And this is why the I and J thing is particularly useful, because you could work out 2 triangles and do awkward stuff.
You could do that, but instead you can just add these things together, the I and J's respectively, and that'll be the answer. So it's much quicker, much easier.
So you've got 6i minus 2i is 4i.
And then you have 7j plus 10j, which is 17j.
And like I said, the questions aren't normally asked like this, but this idea that you can just add together them when they're in I and J form,
Yeah.
you drop your rubber on the floor,
Yeah.
but then also you can answer
Quite
other
handy.
questions.
And we're going to use this idea of resolving vectors when we resolve some position vectors.
So, if I gave a formula,
Right.
we'll call it R, doesn't matter what it's called. Jim Bob. Give you a formula for working out a position vector at particular times.
Okay.
It might look something like this.
Yeah, this could be something like raising and falling of tides, or how a plant grows, something like that. Doesn't really matter what it's about, but it could look a bit like this.
It could. So we've got an amount of I and an amount of J.
Okay.
And that will give us a position vector at points. And if I told you,
Right.
or if I asked you, what's the displacement between, let's say it's a plant,
Okay.
between t equals 5 and t equals 10. And if it's a plant growing, these are probably days, 5 days and 10 days.
Yeah.
Between t equals 5 and t equals 10, what's the displacement between the point then and then?
So when you're talking about position vectors, this is an important point to kind of add here. It's always from the origin. So you can think of it very much like a graph here.
So at the point t equals 5, that will give you a position vector somewhere on the graph. We'll call it A. And at this point t, it will be different. You put in a different value of t, it will give you a different answer. So it'll be a different position, let's call it B.
Yeah, this might not be how it is, but
Might not
say
be how
it's
it
here.
looks. And then you want to find the distance between the two. That's
Yeah.
what we're doing.
So then essentially there you'd do B minus A
Yeah.
in this scenario.
You would indeed. So let's put in t equals 5 in blue.
Okay,
And then
seems
you
to
can
be blue.
find some sexy colour to do B in.
Oh, alright. Oh,
So t equals 5. 5 squared is 25 amounts of I, plus 4 minus 5 times 5 is 25, and that's amounts of j.
Yeah,
so then
so-
overall, the position vector,
Yeah, we get at the end is 25I plus, well 9 minus, sorry, 21J.
so on this graph that's 25 this way and 21 down.
Yeah, so
It's actually down here is our A. If you wanted to draw a sketch,
you wanted to,
it
how would you
might be
think?
useful.
Often it is quite helpful to draw a sketch. We do the same with this value.
Pardon me, that A is not complete. There we go.
Okay.
Carry on.
So then we have over here, look, 100I.
It's t squared, t is 10 at this point.
Yep.
And 4 minus 5 times t is 4 minus 50, and that's an
Yeah.
amount of j. So again, we're going to get another position vector at the point t equals 10.
So we get 100I
minus 46j,
Yes.
which on the graph is much further along to the right than this A, and
Somewhere
further down.
where you can't see.
Yeah, way down.
Okay, but you still do a similar thing to this.
We will indeed.
So
The B is so much further away than the A.
yeah,
Makes
from
sense.
the origin.
when it makes more sense with a picture.
Mhm.
So we've got this 100i
Minus
46.
46j.
Let's put
4j. Yeah, 46j. And then minus, and like we did before, you can just minus the I from the I and the j from the j.
Be careful of your positives and negatives at this point.
Yeah.
So 100 minus 25.
That one's easy, that's 75i. The next one is a bit more tricky,
Minus 46 minus 21 is minus
Yeah.
46 plus 21,
which is 25.
which is minus 25.
Sorry, yes.
J.
That's fine,
Careful
absolute
of your
value.
positives and negatives.
Yes. So that would be how far away it actually ended up, or how much it actually grew in this time.
And that's it for displacement with I and J. If you're still a bit confused about I and J components, we do 2 more videos. The next one's velocity, and then after that's acceleration.
And I and J is involved in all of those.
Yep.
So until then, I think we should practice that game.
Yeah, I mean it is the racket's fault, but I
pretty
feel like I
sure.
should practice anyway.
Yeah.